Hey everyone, my name is Bapi Vinnakota. Welcome to the panel on data center power efficiency. We have three distinguished guests, Tawfik, Brijesh from Microsoft, Tawfik from AMD, and Jonathan from Koomey Analytics. And roughly the plan is, I'll let them introduce themselves. They're all very distinguished guests. As a part of this, there's something about rating themselves on a log scale, so you should pursue that during the questioning. I will let them introduce themselves, but our agenda, our plan roughly for the next 40 minutes is to spend some time going through slides, and as audience members in the first panel after lunch, at least a few of you have a big responsibility to ask a question that just jolts everyone awake. So it's very important. So I think on the broad outline of covering data center efficiency, we will go first to Jonathan, and then to left from your left to your right. Okay? I'm going to get out of the way and let the experts speak.
Okay, I'm John Koomey. I've been studying data centers and their efficiency, energy use, performance for about a quarter century. And it's my job first to set the stage for the discussion. Oh, yeah. Okay. So as many of you know, the workloads for AI have been growing very rapidly, particularly in the last year or so. And there appear to be certainly evidence that there is an increase in electricity demand related to that change in the service demand. And that's something that has a lot of people worried, and they're starting to think about what it might mean if we have this explosion in the use of artificial intelligence. One of the projections that I found recently is by Schneider Electric. And they did what I think is one of the more credible analyses of this. There's a lot of wild projections, people talking about electricity used of all IT going up to 20, 30% of electricity use. That's all nonsense. And I've been through now 4 or 5 cycles of these kind of exaggerations. So just for level setting, the latest data for 2020 shows that data centers are roughly 1% of the world's electricity. Networks, telecom, broadband, another little more than 1%. And then about 2% of the world's electricity is ICT end user devices. So that's where we are, more or less, about 4% for everything. Computers, everything. AI, according to the Schneider Electric analysis right now, is only about 10% of data centers. So the data center electricity use of that 10% is AI. That's growing really rapidly, but even if that grows tenfold, that's only a 1% effect on total electricity use. So people need to keep that in perspective. ICT is not going to be 20%, even 10% of the world's electricity. It's just not anytime soon. So that's something that people need to keep in mind. It's also important to understand the drivers of electricity used for computing. And there are 3 typically. One is the growth in the service demand, how much we want to use AI or any other computing service. Then there's the growth in efficiency. So as the service demand goes up, the efficiency of provisioning that also tends to go up very rapidly, offsetting in whole or in part that service demand. And then the increase in AI will decrease demand for other IT services. So all 3 of those things are deeply uncertain, and we will understand, I think, more in the next few years as to which of these factors will be the most important. Now, we were asked for this panel to talk about 2 important challenges that we see facing the industry, and I chose these 2. The first is the understanding that as the benefits of shrinking transistors has slowed down, as Moore's law has slowed down, we're being forced to look up the stack. We're being forced to look at hardware architecture We're being forced to look at algorithms and forced to look at how we design software as ways to get performance and efficiency improvements. So that to me is one of the top challenges, because we've got to change the way the industry has traditionally operated, basically relying on Moore's law and not worrying so much about the other things up the stack. The second important challenge that I wanted to raise for you is related to existing data centers. And the challenge is that most data centers have a huge amount of stranded capacity, typically 30 to 40% of capacity that just can't be accessed. We were also challenged for this talk to say, well, we're going to identify these issues. Here are at least some solutions that could deal with those issues. So for the first one, for OCP in particular, focusing on OCP initiatives, standards, and research, focusing on workload classes, for example, AI, machine learning, scientific computing, search. As we move towards more special purpose computing, optimized for specific workloads, there's going to be more and more focus, and the more OCP can push people towards thinking about optimization by workload, the better off the whole industry is going to be. On the second challenge, another thing that OCP can do is to push on the manufacturers to develop IT libraries that have the detailed characteristics for each piece of equipment, because that's the only way you can create a digital twin, which is what you really need to manage the stranded capacity. In order to optimize the operation of the data center, you need to be able to model it by physical principles. And to do that, you need these libraries to do that in a sensible way. So this is from an article in Science. It talks about how there's plenty of room at the top. In other words, as you move up the stack, this is where the benefits for performance and efficiency are going to come. And this is a very different way of looking at these issues than has been traditional in the industry. And then for digital twins, most people are familiar with their use in the design of equipment and the design of data centers. But there's been movement towards using the same kinds of tools for the operations of data centers. And this turns out to be critically important because rules of thumb just don't work when you're dealing with airflow. You absolutely need to model the physics. And to model the physics, you need standardized libraries of IT equipment so you know exactly how the air flows and the inlet temperatures and the power relationship to utilization, all that stuff. And so people need to start thinking about how to create a full range of these digital twin models so that you can actually model the entire data center starting from the chip level going all the way to the data center operations. So with that, I will turn it over to Brijesh.
Awesome. I got this. Thanks, Jonathan. So first of all, thanks everyone for spending your time here. I know everybody's starting to think about their flights and all that, so I really appreciate you coming here. So I'm Brijesh Warrier. I'm an engineering manager in Microsoft. I work within the Azure group, and I focus on infrastructure efficiency. So I'm going to build on what Jonathan kind of talked about. Like he kind of proposed this challenge of like, how do we meet this explosive demand for power, like especially with this acceleration in AI and demand for GPUs. So I'm going to talk about like how Microsoft is approaching this problem. So I'm going to kind of step into that. Like, so as everybody's aware, like Microsoft is on the thick of things with the whole the LLM craze and the associated demand for GPUs and the demand for power to satisfy that. And so like my group, like in collaboration with different teams at Microsoft, we've been focused on what can we do to more kind of efficiently and sustainably meet that demand for power. So broadly, like again, like I think Jonathan had touched upon, like where we're hitting limits on how much we can efficiently do at the hardware layer. So we need to start looking higher up in the layer and figuring out ways in which we can run the data centers more efficiently. And so like at Microsoft, we're taking this notion of what we're calling as a software-defined data center. So the way to think of that is, so it all begins with like cross-layer optimization. So we want to basically partner closely with the data center design, partner closely on the hardware design, and then leverage those things in software and maximize how we use power in the data center. So like this picture is kind of trying to capture this notion of like, so you have like the workloads on top, and then the workloads are trying to find resources like data center space, or like on the lower side, the data center space and the power, what was that? Oh, yeah. No, I was just trying to, sorry, point to those things. So actually, I can just maybe show you. But anyway, so I think, so the whole idea is that we're trying to use like a combination of software and ML to better understand the workloads. Like, so we want to get a sense of what workloads are more power hungry, what are their usage patterns, and so on. And then we also want to have a software representation of the data center. So we want to understand what are the power constraints. I think like Jonathan had alluded to the stranding of power. Like, so we want to represent the data center power hierarchy in software, understand the characteristics. So leverage all of that to then more optimally place the workload, have some safe oversubscription and so on to maximize the use of power in the data center. So I'll just touch on like a few kind of initiatives that we have driven. And a lot of these initiatives, we have published papers and we've kind of shared this broadly. So the first, like one thing that we've been driving is this idea of like safe power oversubscription. So like as you all can kind of envision, like if you look at the power hierarchy, as you keep going higher up in the hierarchy, through statistical multiplexing, you see that there's a lot of slack in power. So what we've done is we've built systems that kind of understands the slack. We can look at historic data and then oversubscribe. So you basically deploy more capacity than what we expect the allocation is going to be. And then we have these software systems that can very closely monitor the utilization. And when we see that we're hitting certain thresholds, we can take mitigative actions, like a combination of things where in extreme cases, we might have to throttle this CPUs, but we also have some things we can do because we understand the workloads where we can limit like certain VMs which we see are like, they can handle being kind of turned off or paused. That's one initiative. Another initiative that we've been driving is this. So if you look at a typical data center, when you want to have like 5 nines of availability, what ends up happening is we hold back a lot of reserve power. Think of that as like kind of turn space to deal with certain outages. So what we did was we went and started allocating into that reserve power, and we manage availability in software. So now you can imagine that the whole data center is fully allocated, and we have a certain outage where we lose an UPS. We have like a software system that can step in, and it understands like, oh, here is a set of workloads that are fault tolerant that I can shut them down for that period of time, and then we can wade through that. So things like that helps us like get almost like 30% more power in an existing data center. Similarly, like some other initiatives, like I kind of touched on this, like using ML to better understand workload, use that to optimize our placement. Then there are like a few things that we're driving on like the sustainability front. So one of the things that we're really excited about is this idea of like a grid interactive UPS. So as more and more utilities are trying to switch to renewable energy, so one of the challenges, as you're all aware, is there is periods where you would not, like for example, there's a cloud cover and you don't have enough power. So what we're building is a system where the grid can interact with the data center and send a signal saying that for the next 5 seconds, we need you to shed some load. So what we would do is we would drop the load from the utility and drain a UPS battery. But then we're also kind of extending on that where if we need an extended period of time, we understand workloads that can tolerate periods of loss of availability. So we can shed some workloads and kind of help the grid in that way. And then we're doing many other initiatives like leveraging low power states on the server. When we understand that the workloads are not demanding that much power, we can put them in these low energy states. And there are like a lot of, we're baking in a lot of these carbon aware decision making in the whole workflow, like starting from like supply chain, even like the load placement, trying to be aware of the carbon intensity of the grid when we're placing workloads and so on. In terms of like kind of ask from like the OCP community, I think one is like having standards around energy efficiency, like, and especially as we're getting more GPUs into the mix, trying to kind of catch it early in the designs of GPUs to have that. I think another thing is around like, so one of the challenges we run into is as we onboard data centers, like there is not like a lot of consistency, like especially when we onboard into a leased site, we may not have like standards in how the data center emits telemetry, the latency at which it emits, and so on. Like, so maybe there's an opportunity for the community to come together and define some standards so that like a lot of these software systems can work seamlessly. So I think those were the main things I wanted to land. With that, I'll hand it over to Tawfik.
Okay, thank you, Brijesh. Oh, I jumped right away to call to action, I guess. Yeah, my name is Tawfik Arabi. I'm a power architect at AMD. And I want to talk a little bit about the opportunity and the power distribution and management, if you like, of the IT equipment. I think you've seen a lot of presentations today about PUE of data centers. But generally, the best-in-class PUE is about 1.1. The average is roughly about 1.67. But 1.1 is a pretty good number, right? So you're not going to get nonlinear improvement, even if you go all the way to 1, right? So, and you've seen a lot of presentation about the AI scare, if you like, how much power is going to consume, the rate of growth of AI, and all of that stuff. So the question is, if it's not coming from infrastructure, power savings, where it's going to come from? And certainly, we believe it's going to come from the IT equipment. Let me show you something. Oh. Okay, see if I can get that to click. Okay, so I think a few years ago, maybe 10 years ago, about maybe 12 years ago, there was a big scare about data center power, and Congress actually commissioned this study. There was, they were afraid it's going to take over the grid. And the reason that scare is what you see on the upper side of this curve, the demand for performance. Now, that demand for performance actually turned out to be true and translated, and it continued to be true. But what was also happening is that the semiconductor industry got very, very power efficient, and that's what you see on the lower side of the curve. So as demand actually grew, power efficiency got much, much better, both for the semiconductor and, like I showed you, there was very significant improvement in PUE of data center, and that buckled the trend. And we've seen over that decade a modest increase, yearly increase in data center power. So we believe the next breakthrough, if you like, to buckle the trend again, is also going to come from the semiconductor industry. And AMD has already, announced a goal to improve 30x in power efficiency of its product on the GPU and CPU sides. And this afternoon, actually, I have a paper. I can show you how we're doing, but in a very short summary, it's actually so far doing, a little bit better than the goal. But there's another area I want to point to where I think potentially, we can get help from OCP, and another area for power savings, and primarily in the power distribution and power delivery. Let me show you some examples. Just an example, okay? I'm going to call it theoretical example. What you see on the left here, or right, depending where you're sitting, but is this CV squared F curve? That's a curve, basically, of power versus performance. And roughly it says, okay, if I'm willing to give up 20% of performance, then I'll get 50% of power, okay? So you use that concept and you go to this side. Oh, I am actually, no, I went, oh yeah. This side, and you say, okay, what if I break this, for example, 100-core CPU into 2 chiplets, each one of 50 cores? And assuming you don't need performance on every one of those cores, and you dedicated those 2 complexes, as different performance and power level. If you're able, for example, to give 20% performance here, that's 50% power. So that's 50% of 50%. You save roughly 25% of your total power, which is very, very significant. Of course, you introduced more complexity, hardware complexity, because you have now multiple power domains within the same CPU complex. And you introduce software, also complexity, because now your allocator software has to recognize those cores as different. It has to understand its power and performance characteristic. Now you can imagine, this is 2-power domain. You can imagine, well, why not 100 power domains? And of course, the complexity gets a lot harder, both on the hardware and the software, and the power savings get more. Okay, let me go back here. And the other one, I think, in the power is primarily the redundancy in the power distribution. So that's primarily driven by availability in the data center. So the management between average power and peak power is extremely critical. Because if you look at peak power, typically it's at least 2x your average power. And if you look at redundancy in the system all the way to the utility, because data centers don't want to have any failures. So they tend to duplicate that hardware. So you'd think I'm roughly maybe 4x, I'm provisioning hardware than what I need for my average utilization. And narrowing that gap, I think, can be very significant impact, particularly on sustainability. What do we need? Where can OCP help? That's a question I think we're all asked, to answer. So if you look at the fine-grained power delivery, for example, the software has to understand that and leverage that, right? Which means you have to communicate all that information to the software. Each core or GPU or compute units on those GPUs have to communicate their power states, have to also communicate something about their budget and their power budget to the software. And developing standard, I believe, around that can be very helpful. So I think with that, let me just, summarize with a call to action. And this is on behalf of my colleagues and myself. Like Jonathan was saying, OCP should, we believe, organize all effort by workload type to facilitate workload-specific optimization, special purpose computing, and co-design of software and hardware. OCP should push IT industry to create IT library for use by digital twins. Like I showed you, we believe a lot of that, the semiconductor industry need to continue on the trend they had over the last 10 years in terms of power efficiency. And we need everything, we can get. We need standards, for example, around power communication, different components communicating their power budget. We need smart power allocation. If GPU is not using all the power and it can give some of that budget to memory or vice versa, we need communication protocols. We need standards on how that communication is done. And like my colleague Brijesh was saying, we need standards around benchmark and a benchmark and efficiency profile on GPU system and also on power telemetry, basically. And I think with that concludes my side, and I think I'll hand it back to you, Bapi.
Yes, sir. All right, thank you. So we had a bunch of prepared questions, but I think I'm going to throw all of those away and ask one of my own separately, but I'm really hoping someone in the audience has some on any of the concepts that our panelists have spoken about, power efficiency. Okay, please.
So what I've noticed today is that all the leaders of the working groups tend to come from big companies. And for example, if you take the PUE, that's a metric that promotes large scale. The bigger you build your data center, the easier it becomes to reduce your PUE because the overhead of the IT facilities, of the non-IT facilities can be spread out over more computes. So would it be beneficial to have leaders, people from small companies, startup that maybe think like small companies in the context of this sustainability track?
Anybody like to take that? Well, as a small businessman, maybe you should take that.
So I'm not quite sure what you're asking. There are real economies of scale for this, and that's been traditionally the advantage of the hyperscalers, is that they've had this economy of scale, this ability to have big teams of people attack these problems and really improve things. I'm not sure that I mean, obviously you need to have entrepreneurial focus on these questions too, but a lot of the benefits, a lot of the efficiency benefits are going to come from scale, and then also having the big companies have many more users, many more kinds of users. So they're able to have much higher utilization for their equipment, and that turns out to be a critically important part of sustainability. If you think about it in terms of compute delivered per watt or per kilowatt hour, the utilization turns out to be a critical part of it. And that, again, it's an economies of scale thing. So I think a lot of the action is by the big guys, and for good reasons.
Yeah, no, and I think also if you directionally look at the percentage of deployments, majority of them happens to be on the hyperscalers. So I think those being efficient helps with the broader piece. And I think the smaller companies probably just have smaller deployments where they're concerned about not having to put their data in the public space and so on. So I think it helps that the hyperscalers are operating at a very efficient PUE, and that being a bigger part of the deployment.
I just realized, so there is one area where there are specialized workloads that are relatively small. You could imagine innovations coming from companies in those specific areas. And what we're seeing is extremely powerful benefits of this kind of co-design of software and hardware. And in the paper that I cited there, the Lyserson paper, they show a factor of 60,000 improvement in choosing algorithms and improving the software. So we're talking about many orders of magnitude improvement, and you could imagine for relatively small workloads, there would be opportunities for small companies to do really well in a very narrow niche. So that's an area where I could see smaller companies having a big opportunity. Okay.
Yeah, thanks. This is Eric Dillon from Intel. And I wanted to talk a little bit about, so you kind of put in a plug for something that we talked about this morning about needing telemetry for energy utilization, kind of real time out of the system, in out of the power delivery subsystem. But there were 2 points made here, I think, from Azure about trying to overcommit the power in the rack and make that a safe thing to do. And then Tawfik talked about trading performance for efficiency potentially, if that can be done. To do that, it seems like we need a couple of things that we have resisted historically, right? So first, we don't just need telemetry. So I encourage all of us to work together on the metrics work group and on the telemetry work group, the projects we already have going, to get the right things up there so that software gets what it needs. But we also need a capability discovery, it sounds like, and that's been a tricky place, right? So we haven't even seen decent NUMA optimization, right? So we're kind of proposing that we go back to, we had been on an excursion towards portability, where you want to be hardware agnostic, and now we're trying to pull people back to hardware aware, both with specialized compute and with these ideas of, what capabilities exist. Can you talk a little bit about your thoughts on how we can foster kind of support for that, hardware aware instead of hardware agnostic change in the software layer, and kind of what kinds of things you think we need to make software aware of? Because we didn't talk about time constants here, but that's where the devil is in those details of if you want to ride through or operate off of a battery when the renewable energy has a hiccup, right? You need to know what's possible so software can make the best decision. That means we don't just need the telemetry, we also need to know what the capabilities are and the responsiveness timescales of those capabilities.
You want to try? Yeah, I think if I get your question right, you're asking, what type of capability we need to have in the hardware, and in the context, at least, of the example I'm saying, it's more like being able to, for example, communicate, like in the case of these different cores, for each core to communicate, hey, I'm capable of that much power that much performance, for example, you know. So give me more voltage, give me more, you know, give me more power budget, basically, and I can do more work, or vice versa. On the time scale, I'm not sure exactly, you know, I got your question. Maybe you want to try.
Yeah. Yeah, no, so I think on the telemetry and the time scale piece, like I think there's like two kind of dimensions. So I think there is something at the server level where you probably, like, so for example, I talked about when we see that we have exceeded some power budget at like a rack level, we send a signal to the server and we need to take some actions there. So they're having like a very fine-grained telemetry on like which cores are consuming more power, and even like ideally if we can, like in our case, if you can map it back to the VMs, it helps us make like very like selective decisions, like, oh, this certain VMs that we can tolerate being shut down. So it kind of helps us make that decisions. But at the higher layers, then like it's at a much larger time granularity, like at the rack level, row level, like at the data center level. So those would be like in like second, close to a second. And on the server level, it'll be like microseconds, like much finer granularity. Does it make sense?
Thank you. I think we need some guidance. Tawfik and I both work in the silicon side, right? We got to focus on the features that actually will make a difference to the exclusion of the features that wouldn't have been used anyway, right? To get the right things above the line.
Makes sense. Thanks.
Hi. Jonathan, you and Tawfik both mentioned digital twins. And I was looking for a little bit more detail on what's the connection there and how do they play in. Digital twins of what, and what would they lead to?
There's a long history of the use of digital twins for design, for all kinds of industrial equipment. So in essence, the idea is that you create a digital representation that is exactly the same in all the ways that matter to the physical device, right? And so for design, it used to be when they designed the boxes, they would actually make cardboard models to figure out the airflow. Now this was back before, before we had a lot of computing power, right? But then they realized they could use CFD software to do that, right? And so everyone's familiar with that use of digital twins for design. But the new concept is to use a digital twin actually for operations in a data center. And the reason is that you design a data center with a certain distribution of loads. You say it's a 1 megawatt data center. Unless you put in your IT power loads exactly as the designer specified initially, you will never have a 1 megawatt data center because the airflow, the cooling, the space, the power all get fragmented. And so unless you exactly match how it was designed, you're stuck. And so in order to anticipate that, you can do a model of the data center, and you can then anticipate, if I put this equipment here, this is what's going to happen to airflow in the rest of the data center, and avoid the hotspots, avoid the problems ahead of time. But you have to do the modeling. You have to create a model, you have to calibrate it, and you have to make sure that it's kept up to date. So it's really an operations use of a digital twin, which is, it's not done very often. Certainly not done enough.
No, I think he covered it quite well. Thank you.
Hi, my name is Ray with Microsoft. I had a question for you on this new term, the IUE, the infrastructure utilization efficiency, and this goes to your comment about stranded power and so forth. How useful is that metric, and how should we be using it in order to tune and target our data center implementations?
Yeah, thanks, Ray. So I think Ray's question was, so everybody's aware of the PUE, which is basically like, it's an indicator of how much of the power is being used for non-IT load. And so IUE is basically like this notion of, so once you allocate the power for the servers, how much of that is actually getting utilized? So once you get to the IT side of that power equation, how is it efficiently being utilized? I think it's definitely a very useful metric, and we actively use that at Microsoft. So I think one of the challenges that we run into, like in the cloud space, is that when you deploy customer workloads, so like you can imagine, we design like a like a Skylake-based system, and then we're trying to deploy it in the data center, we need to estimate how much power it's going to consume at the rack level. So we could run like benchmarks, or in extreme, you could look at the TDP and design the rack for that. Obviously, we don't do that, but then it's like, because when customers can decide to choose to run any kind of workloads on our VMs, so there's a lot of variability. So we'll have to make some level of speculative thing on what the number is going to be when we make these allocations. And if you get it wrong, you would have allocated, let's say, in 20 kilowatts in a rack, and we're only using 10 kilowatts, so you end up with significant inefficiency. And so IUE helps measure that. And so then we use that metric to then identify where are these opportunities for us to either like have a feedback loop on how we maybe be more aggressive in our rack allocations, or can we harvest that power and deploy additional capacity in different parts of the data center. So yeah, so
I just want to make a more general comment about utilization, because I think there's a lack of connection between the technical knowledge of the people in the data center and the business choices that companies make. And we need a whole lot more visibility into utilization of all parts of the data center, so that the financial people can know. Like if the CFO knew that 30 or 40% of the capacity of the data center was useless, heads would roll, right? Things would change. But right now, it's invisible. So this specific metric has certain applications. As Brijesh said, there are other ways to measure it. But there's this higher level issue of bringing visibility to the financial people who are making these investment decisions, so that we can use all of the data center equipment to fullest advantage. Because as far as I'm concerned, we should be getting as much compute out of the money we spend as we can. Just capital efficiency.
Tawfik, you want to add anything? Okay. We're down to 3 minutes. Any additional questions? Oh, we do have one. Awesome.
You had a good point about maximizing the value you're getting out of the power, basically. But do you think what will open people's mind to like that kind of waste is when power is going to get constrained, and basically for the cloud players, your region, you have pretty strict restriction, and people are going to be like, well, it's impossible to add another 200 or 300 megawatt year, so we'll need to use the 300 or 400 megawatt of waste we have in our infrastructure. Where do you see that happening? Or
so the situations where there are real constraints, that's obviously strategic. It raises the strategic importance of these kind of issues. Ideally, you would have companies starting to realize, the financial people starting to realize, that they need to more fully understand the value that their IT investments are delivering. In order to do that, you have to be able to map IT investments onto business processes. And most companies do not do that. There's a thing called the TBM Council, and it has this whole taxonomy that you can use to do this kind of mapping, but most companies don't do it. And until we get to the point where IT is not a black box, where it is a thing where people can actually say, I spent this money and I got this return on the IT investment, it's only going to be those emergency times that you talked about that people are going to focus on it. But we need to get to the stage where we're actually getting the real business value and knowing what the real business value is from these investments.
Just a follow-on question, because my perspective is that people are actually aware of that, but they're actually choosing less efficient equipment and stuff to actually minimize capex. And if you see it so I'm in a wholesale colo business, not an I-build facility for some of you guys. And what I see is you're signing contract with people with 1.4 PUE and crazy stuff like this. So the financial people are aware of it, but that kind of trade-off is actually made by them, don't you think so?
Well, but this last thing, they're aware of the PUE. They have no idea that the utilization of their servers is terrible.
Yeah, I think another thing that can help is basically, there's a lot of focus, like you said, to me, I think, performance and cost. And there's a lot of, power scare that drives people, toward that efficiency. But performance always comes top. and then cost. And the other thing, I would like to see, for example, this is where OCP may be able to help. Like if I'm a consumer and I can go today and check, for example, AWS versus Azure, I can compare performance, but I can't compare anything about power or energy efficiency. And if there were a metric to get consumer awareness, actually, I think you might see a little bit even more interest in people willing to pay kind of for that power efficiency. And that's an area I really think OCP maybe can drive. Something like the equivalent of an Energy Star, like, on laptops. People paid more money for that, basically. And I think if somehow you can, read that out in whatever VMs, and I can compare those not only versus their performance, but versus their energy efficiency. I think that could help as well. You want to add something?
Yeah, just on one point on the question, I think the companies kind of need to look at like a TCO of running a server in the cloud or like in the data center. So I think you're talking about only looking at the CapEx, but I think if you try to think of like the hosting cost of running in the data center, energy and all of that, I think that'll hopefully help with making better decisions. But to Tawfik's question, I think we definitely see like a kind of a pull from our customers to learn more about the carbon footprint of their deployments in the cloud. And Microsoft has definitely started doing that. Like, so we have these emission dashboard where customers can go in and see, like, for a given VM that they deploy, what was the carbon footprint for that? Or if you're planning to consider using Azure, you can come in and say, like, oh, if this is my profile of my deployment, it can come up with some estimate of their carbon emissions. So it seems like there's a push coming, and maybe there should be more of that.
All right, we're at a scheduled time. I don't see our next panel, so maybe can we take 2 more minutes, or anybody want? I'll ask the panel to close with, if you're here next year at about the same time, what would have changed from now to then? Maybe close with each of your predictions, and then we.
Tawfik, why don't you go first?
I think probably would see a lot more power grids go off because of AI. I don't know, but I'd like to see, how those trends are materializing. I'd like to see the consumption that AI is driving, the power consumption. I think it's real. I think that power increase is actually real. But I'd like to see a little bit more. I think there'll be more awareness. I mean, if you look at, NVIDIA doubling their sales and all of that stuff, that's a pretty good indication. But I'd like to see what's being done, about it.
Yeah, I mean, I think I expect like a continued acceleration in the kind of growth of GPUs and the associated power demand associated with that. And so I'm assuming like next OCP will probably be like lot more GPU focused sessions and booths and so on.
Yeah, and I'm pretty sure that by a year from now, we're actually going to have real data on how much electricity is being used by AI and other parts of the data center system. Lawrence Berkeley Lab is doing a study that should be done by the end of 2024. Report to Congress is the 3rd one. And so we'll have real data by then, and we can hopefully tamp down a little bit of the hype that's going around.
All right.
Thanks.
Thank you
Thanks
all.
Everyone.
Well, I was going to say, just buy AMD GPUs and it'll fix itself. Yeah.